3 of this series on functions at the higher level. In this tutorial, I want to talk about thinking about a different argument in a function and the related topic of composite functions. And for this, it's very helpful to have that mental picture of functions as a machine which is operating on an input. Students often find these topics difficult, and I think the reason is because they get very caught up with the symbols, particularly x and f of x. So the key to this will be to free yourself of the sort of symbol addiction, I think I called it in a previous tutorial. So let me show you what I mean by that. So let's just think of a function, but I want to use the kind of machine picture of a function. So here's a function. It's a box, a black box with a big label on it. Okay, and the label says F for function. And there's a pipe that comes in, and that's the input. And then there's a pipe on the other end, and there's the output. And let's choose for our function x squared. So f of x is x squared. Now do you notice then when I said let's choose for our function x squared, that's because we sort of use x as the default argument that goes into a function, that is the input. And so we always like to think about x, but actually it's just a shorthand, and really it can be any noun or symbol that you like. What we're talking about are real numbers, some real numbers coming in, it's being operated on, and then a real number is being sort of spat out, if you'll excuse the expression, outputted by the machine. In this case, whatever you put in is getting squared. But you see, the reason one can get confused is one might have a question along the lines of, given that f of x is x squared, write an expression for f of 2 minus x. And all of a sudden one can start to feel a bit uncomfortable because one thinks, well, hang on, f of x is x squared, now I've got 2 minus x, where do I go from here? So let me indicate the way that I think might be helpful to think about this. It's going to sound a bit silly, but I think it's quite helpful. Remember, x is just a symbol, convenient symbol that we use, but what actually is important here is the definition of this function. In this case, think of it as a machine. Whatever you put in, and I'm going to put in an apple symbol, then this machine will take whatever you put in and multiply that thing by itself. So out will come that apple symbol squared. And that's what this function does. And now I think you'll see it's a bit more straightforward to think of this question. Well, f of apple is apple squared, and I can substitute for apple anything I like. In this case, it's the expression 2 minus x, so f of 2 minus x, I'm thinking of this as my apple, I just have to square it. So it's that expression all squared, and that would be the outcome of that. Let's do another example. Let's imagine we had a function that was defined, and you see we nearly always use x as the default to define a function. Let's say we had a function f of x defined to be, what shall I choose? Let me say it is 2 minus sine x. That's my function. And what I would recommend is that you immediately think, right, f of apple is 2 minus sine of apple. So whatever the input to this machine is, the output is that that thing gets put into a sine function and then subtracted from 2. And then if you had a question, what is f of, let's say, 1 minus 3 over x, which looks rather ugly, then, okay, this is the thing that we're interpreting as our apple symbol. And so this would equal 2 take away the sine of 1 minus 3 over x. So I hope that's helpful in sort of, wrenching our minds away from the constant f of x, f of x, f of x, so that you're quite comfortable if you're given a function, and you'll nearly always be given a function as f of x equals some, expression involving x, that if you have a different argument of the function, a different input to the machine, you just regard that as an expression. Think of your function as f of apple equals some operation on this apple symbol, and then whatever expression you have, that is essentially the apple, and then you just operate as we've indicated here. Okay, so in this case, for example, just regarding 1 minus 3 over x as that apple symbol, we know how to write f of apple, as it were, down in terms of that apple symbol, and we just substitute this expression for the apple. Quite straightforward. Now, a related topic is this idea, to be a bit more formal, I suppose, about what we're doing here, is called composite functions. And what I'm going to do is just show you how this might look in terms of the mapping idea that we talked about with functions, and then again in terms of machines. And then what we'll do is just a couple of quick examples. But to be honest, if you're comfortable with this idea, you'll find this composite functions topic relatively straightforward. Let's have a change in color of pen just for variety's sake. So let's think about our sets that we talked about. This is the more formal way of thinking about functions. And we have a set x, capital X, the elements of which we label as little x. We can think of another set, capital Y. These are sets of real numbers. We have an element here that we'll label as Y. And there's a mapping that I'll draw in red between set X and set Y, which we will be unoriginal and call F. Now what we can do is think of a third set, and let's label that by Z, or Z for our American friends, our American viewers, and an element of set Z or Z we will label with little z or z. And there'll be a mapping now, we can imagine, between set y and set z, and that mapping or that function we will describe by g. Okay, now what we can write here is that y is obtained by applying the function f to x, and z is obtained by applying the function g to y. But we can also imagine that there is just a direct mapping between set x and set z, and that there is a mapping that just takes you straight from element x to element z, and let's call that capital F. Okay, in which case we could just write that z can be obtained immediately by applying this mapping f to the element x. And what we can do now, you see, is relate this function capital F to little f and little g very straightforwardly. We say, well, we could get z by applying capital F, some function to element x. Alternatively, we could get z from applying the function g to the element y, but remember y we obtained as applying the function f to element x. And then you see we have this idea of a composite function. Capital F is a function in its own right that maps the set x to the set z, but it can also be thought of as a composite function where we have a sequential application. First of all, a function f to x, and thereafter application of another function g to f. I'm going to give some examples of that in a second, but I just want to draw this picture in the machine form, in the machine language, if one was making a very small computer science joke. So let's see how that would look. We would have a machine with its kind of input and output, and let's call that machine F. And then the output would go directly into another machine which has its input and output, and let's call that other machine G. Okay, so in our language you could put in, for example, an input in here of x. The output is f of x, which for shorthand we'll call y, but that y just gets fed straight into this machine, and out comes something we're calling z, and that z is g of y, and y in itself was f of x, and so we have g of f of x. But at the same time, we could just sort of put a black box over this whole machinery here, and then you just have x coming in, z coming out, and you could just, if you wish, call that whole machine inside the black box capital F, and you would have that z is just capital F applied to x. And it just, again, completely equivalent picture to the more formal kind of mathematical picture of sets, mapping sets of real numbers to one another, or this more sort of operational view of functions, thinking about two functions, two machines here in sequence. The machine picture is helpful in terms of sort of thinking of the functions as being an algorithm or an instruction that acts on an input. So let's just do a couple of quick examples here. So let's imagine that we just define a function, f of x is, let's say, 2 plus x. And you can think of it as a mapping, or you can think of it as a machine, whichever you wish. And now I'm going to define another function g, but I'm just going to use x as the default argument here, okay? And it's going to require us to be quite strict with ourselves, not getting too addicted to getting worried about x. It's just there to say that yes, there is some argument to g. Let's say it's sine of x. And then we can think, well, what would the composite function be? F of g of x, for example. So what would this composite function look like? Well, the way you need to think about this is to say, right, I know what g of x is. G of x is sine x. Now, f of g of x, right, think f of apple, as it were, is 2 plus apple. And this g of x here is sort of playing the role of your apple. And so f of whatever you put in is just 2 plus that input. So we have 2 plus, and then the input is g of x, which is sine of x. And then similarly, you could think, well, what's g of f of x? Well, in this case, you think, well, I know what f of x is. It's 2 plus x. g of f of x. Okay, think of g of apple is sine of apple. So the g function just takes the sine of whatever the argument is. So the g function says sine of the thing that you feed to me as a machine, and what you're feeding to me is f of x, which is 2 plus x. And so those are nice examples where you see the difference of f of g of x and g of f of x. We're nesting those examples in the opposite ways there, and you see we get two very different functions that come out as the composite function. So when you're dealing with composite functions, clearly the order in which you take the functions is absolutely critical. So let's just do one more example of composite functions just for practice here, and I'll go through it a bit more quickly. And I'm going to be, very sort of boring here and just write f of x and g of x, because that's the way you'll nearly always be given these problems. And the message of this tutorial really is not to worry about x. That's just a placeholder. It's really telling you, as a given input, what's the algorithm that gives you an output to that function. Let me just make something up here. Let's say that we have f of x is 2 over x squared. And let's say we have g of x is, 3, take away the square root of x. So two rather unlikely functions that we're going to combine here. And let's think about f of g of x. Okay, well, g of x we already have written there. F of something, f of apple, is 2 over apple squared. So it's 2 over the square of whatever the argument is. And that argument is g of x, which is 3 take away root x. Not a very attractive function. There's no real way that you would want to simplify that, I think. And then on the other hand, you'd have g of f of x. Well, let's see, f of x is just 2 over x squared. G of its argument is 3 minus the square root of the argument. At the risk of being boring, we could say g of apple is 3 minus the square root of apple. The apple here is f of x. So we have g of something is 3 take away the square root of that something. In this case, it's f of x, which is 2 over x squared. And in that case, we might choose just to simplify that to 3 minus the square root of 2 over x. Right, good. I hope that was helpful. For some folks, I imagine you might say this is really just a lot of much ado about nothing. This is actually very straightforward. If so, that's great, and I hope this wasn't too dull for you. I think for many students, though, hopefully this will resolve a confusion that they've had about the arguments of functions and sort of dealing with composite functions, where I think one can get caught up with the symbols, particularly the maddening feature that we keep using f of x. You might say, why do you keep writing f of x? And the reason is, it's just a handy default language to use. It means you don't have to think. When you want to just write down a function, you don't have to think, oh, what symbol am I going to use? You just, by default, typically use f of x, because actually the essence, the point of it, is the form of the function, not the symbols. That's why we keep using f of x, because it's the form, not the symbols, which contains the interest, whether it be in maths or in science. That therefore, though, does require a discipline in manipulating functions where you have either different arguments or you have composite functions, where you just need to back off a little bit from the symbols. And I've got this kind of jokey way of trying to explain that by just thinking about f of apple, which is such a silly symbol and so non-formal that it just sort of reminds you, right, oh, that's just the input to the function, which is sort of like an operation or an algorithm in this kind of picture, more of a computer science or engineering way of thinking about functions. And I find that quite helpful sometimes if I do get a bit confused about what's operating on what. Great. Hope that's helpful. I'm now going to prepare the next tutorial on inverse functions. Then we'll sort of be done with the functions topic. I'm then going to do a separate tutorial on graphs where we'll be thinking about transforming functions. And after that, a very, very exciting new topic. I just can't wait to start making the tutorials on it. Calculus. Amazing topic. Right, so I look forward to seeing you then.